Assalamualaikum and hi. So today we'll enter a new chapter, chapter 3, electric current and direct current circuit. The first subtopic here is electric conduction. So in this subtopic, you are required to understand the microscopic model of current. Sebelum kita tengok pada the microscopic model of current, let us recall back the definition of current here. Current is known as a rate of flow of charge through the conductor, iaitu berapa banyak charge yang akan flow dalam conductor itu in a certain period of time. Okay, so let's say you have a conductor. Conductor is a metal here. Dan kita tahu dalam metal there is presence of free electron. Banyak sangat free electron. We do not have any electrons in insulator. That is why in an insulator you cannot conduct current. Kita tak boleh conduct electricity. Okay, so in the diagram here, the first diagram here shown to you the free electron in a conductor. So these electron are the charge carrier and they move freely and randomly. As you can see in the second diagram here, it shows that the electron here is moving in all direction and it is free to move in any direction. Let's say now we apply an electric field to the conductor. You have an power supply where we know in power supply we have positive terminal and negative terminal, dan electric field akan flow daripada positif ke negatif. So at this particular point, due to the presence of electric field, this conductor yang mempunyai elektron di dalamnya akan experience the force. So all this electron is going to experience electric force. This force is going to lead the electron to move with the velocity known as drift velocity. So the electron is going to move in the direction which is in the same direction as the force experienced by the electron. So kita tahu electron will be attracted to the positive terminal. Therefore, force of attraction dia dekat sini adalah to the right. Therefore, the electron will have drift velocity to the right as well. Okay, and as we know, the current pula flow from the positive terminal to the negative terminal. As you can see here, the electron is moving from negative to the positive terminal, and current is moving from positive terminal to the negative terminal. So we can deduce that the current is flowing in the opposite direction to the electron flow. As I've mentioned before, the electron is going to flow with the velocity known as drift velocity. This drift velocity is the mean velocity of free electron, which is in the direction parallel to electric field. Okay, next we're going to look at the equation of electric current. As you have understood, how does the electron is going to flow here, which leads to the production of current. And current is defined as the rate of flow of charge through the conductor. So by equation, I is equals to dq over dt, where I here is the current, dq is the amount of charge flowing through the area, and dt is the time. The unit of current is ampere. Okay, next we're going to continue with our next subtopic, 3.2, Ohm's law and resistivity. The first thing here is the Ohm's law. According to Ohm's law, the V is directly proportional to I at constant temperature. However, this is only valid for metallic conductor, where mathematically the V is equals to IR, where you have V is the potential difference, I is the current, and R is the resistance of the conductor. So as we know, as they are proportional here, the increase in potential difference is going to lead to the increase in current. Therefore, when I compare this V is equals to IR to my straight line equation, V is equals to mx plus C, I will have my y-axis as my potential difference and x-axis as my current here. So if I were to plot graph of V versus I, I'm going to get a straight line graph here, where my straight line here represent my gradient, which is compared to the equation here gives the resistance. So my gradient here is the resistance. this is only valid for metal, as the Ohm's law itself states that the V is only proportional to I in two conditions at constant temperature and must be across a metallic conductor. If you were to have a semiconductor here, when you plot V versus I, you're not going to get a straight line graph. You're not going to get the relationship between V and I directly proportional here. No, for semiconductor, what you got here is an inversely proportional graph. Okay, next we are going to look at the term resistance that is present in the equation V is equals to IR, where resistance is the ratio of the potential difference across an electric component to the electric current I passing through it. So basically, if you rearrange equation of V is equals to I over R, making your R as a subject, you're going to get V over I. This is what the definition is all about. The ratio of V across an electric component to the current passing through it. Resistance here is a scalar quantity with the unit of ohm. And there are a few factors that affects the resistance of a conductor. The first one is the type of the material it is made of. Next is the length of the resistance. And then the cross-sectional area of the resistance, and lastly its temperature. If any of these four factors that I've mentioned changes, it could affect the value of the resistance. Next, we are going to look at the resistivity. Okay, this is a new term that I'm going to introduce to you. Resistivity, or the symbol for resistivity is a rho, is defined as the resistance of a unit cross-sectional area per unit length of the material. So by definition, a resistivity is resistance of unit cross-sectional area per unit length of a material, which can be mathematically written as rho is equals to RA over L. Rho is the resistivity, R here is the resistance, A is the cross-sectional area, and L here is the length of the material. The resistivity here is also a scalar quantity, as your resistance is scalar quantity, area scalar quantity, and length is also scalar quantity. The unit for resistivity here is ohm meter. And to understand resistivity better, it is basically a measure of material's ability to oppose the flow of electric current.